Node.js is rapidly finding its way into the enterprise, and this means that it has to sit well with other languages, technologies, and frameworks. This is where enterprise integration comes in, and we'll discuss this and lots more in this section. As you may be wondering, what exactly do we mean by enterprise integration? Let me illustrate that with a simple example. So imagine that you have a Node.js app. Let's say it is a shopping website like Amazon. An e-commerce business, thus, would not just be confined to the website alone. There would be other applications such as an email service for sending out transactional mails, newsletters and marketing emails, a fulfillment center software which is used by the logistics team to manage inventory and dispatches, as well as big data analytics and recommendation engines that send you buying recommendations every other day based on your shopping behavior on the site. And it goes without saying that you cannot cram all this functionality into your Node.js app. It's neither practical nor wise to reinvent the wheel in situations where established and elaborate solutions can be made in other languages, technologies, and frameworks. So, for all practical purposes, let us assume that our email service is written in Python, our fulfillment center software is written in Java, and our data analytics engine is also a Java program. In this situation, the Node.js app sitting in the front needs to communicate with this pipeline, and not only that, these highly varied applications also need to talk to each other from time to time. For instance, the fulfillment center software needs to send out order and delivery status mails to the customer as soon as their order ships out, while the recommendation engines need to coordinate with the email service to send out newsletters on a daily basis. This interoperability is what we term as enterprise integration. So before we head out into specifics, let us examine the challenges that you face when you try and get applications written in different languages and frameworks to talk to each other. For starters, they all may have inconsistent APIs that are not designed to talk to each other. This can pose a big problem when you are attempting integration, and not to mention language incompatibilities that come in the way. Another key thing to note here is that more than often, these apps will be deployed across inter-networked but dedicated infrastructure. This can make things difficult as far as efficiency and speed goes. If a certain application is unavailable or is unreachable, data may be lost forever and can potentially trigger a chain reaction of anomalies across the business. And finally, businesses these days need to dynamically evolve, and this also means technology evolves around it. So, if a company wishes to upgrade, rewrite, or improve their fulfillment center software, it might just end up breaking the integration chain with other apps in the ecosystem. All these challenges are real and common, and this is where a rock-solid enterprise integration strategy is key. So how exactly do companies deal with this task? Well, the first and rather naive approach is to use shared data files. In this case, App A, for instance, will write out some data to an XML or a comma-separated text file, which periodically can be read in by App B for its own purpose. This sort of integration is loose and prone to errors. If the file is being written to and is being read at the same time, integrity errors may occur. Also, the data isn't secure and is prone to failures and loss. The next common approach is to provide publicly accessible functions or methods across the apps that may be remotely invoked to pour out data. So App A, for instance, will remotely invoke a function in App B to get some data when needed and vice versa. The biggest issue here is that this process is synchronous for most part and is dependent on a very reliable network. If either of the apps crashes out, it can lead to a number of errors across the ecosystem. Another common approach is to use a shared database, and for most of the cases, this isn't as bad as the approaches we've just seen. In this case, App A and B write to a common database server, and either apps can read from this database as and when they need to. Both apps in this case have to periodically check into the database to see if new data is available or not, and the process may not be real time. In many cases, app A keeps dumping data into the database all day long, and during off-peak hours, app B gets the data and processes it as desired. A lot of synchronization tactics need to be worked into this kind of a solution, and though it's better than the previous two methods, it still is far from being efficient. Finally, we have message brokers, a technique that has matured into quite possibly the most efficient and flexible solution for the job. In the case of message brokers, an asynchronous messaging system, somewhat like an email exchange server, sits in the middle of all apps and does the routing of data across apps. Apps that need to send data to other apps publish their data into virtual queues or topics. Apps at the receiving end subscribe to these virtual queues and they get the data almost instantly. This is also known as the publisher-subscriber model, or pub-sub in short. If for some reason an app is not available, then the messages are stored in the queue till such time the app comes back online again, which is when the delivery is achieved. By deploying a reliable message broker in the middle, not only is data transfer secure and efficient, it is also guaranteed and designed to work in case of app failures, which can be quite common in a large-scale enterprise. So going back to our shopping site example, this is where a message broker would fit in. It would be the designated information superhighway that manages data across all applications. In our case, we'll use the Apache Apollo message queue server to deploy our integration scenario. Apollo has its foundations in the hugely popular Apache ActiveMQ, which is used by some of the biggest companies worldwide. ActiveMQ was re-engineered from scratch, and the result of this is a highly reliable and fast message broker that we know as Apache Apollo. To enable different technologies to talk the same language, there are various protocols that message brokers use, and Apollo is no exception. There is the Simple Text Oriented Messaging Protocol, or STOMP, that we'll be using in this example. STOMP uses simple text-based transfer of data, and there are STOMP clients for all languages and frameworks. Then there is the Advanced Message Queuing Protocol, the MQTT protocol, and many more such as OpenWire. Apollo, like its predecessor, supports most of these protocols, enabling you as the developer to pick the one that suits best for a given scenario. As I've already mentioned, Apollo uses a publish-subscribe model to enable apps to reliably send and receive data. Practically, data is stored on disk using an implementation of Google's LevelDB store, which is a file-based memory store that is fast and quite powerful. For advanced deployment scenarios, monitoring teams can use a simple JSON-based REST API to monitor an Apache Apollo server remotely. Also, and quite importantly, data that goes across Apache Apollo is sent asynchronously, which means that if either of the apps are unavailable, then the data is delivered when the app is available. There is also excellent support for data recovery in case of a crash. Apache Apollo is available on Linux, Mac, and Windows, so you can deploy it in virtually any kind of a situation quite easily. It should be noted here that Apache Apollo or Apache ActiveMQ aren't the only message brokers available out there. There is RabbitMQ and many other solutions from multiple vendors, each trying to solve the integration scenario. Fortunately, almost all of these solutions support standard protocols such as STOMP, so most of the times, if you need to change the broker, it may not necessarily need a change in code as far as the apps go. As long as your apps speak a common protocol, any broker should be good to go in most situations. So, for example, we are imagining a situation where our Node.js app needs to talk to Python and vice versa. Here's what it would look like in a nutshell. In the middle sits our Apache Apollo message broker. The Node.js app publishes the data that it needs to send out to the Python app, as a topic called out queue. A topic or a queue is a dedicated unidirectional pipeline that can carry the data across. The moment Node.js publishes data to out queue, the subscribing Python app receives it. When the Python app has done its processing, it publishes the data back to another topic called in queue, for instance, to which our Node.js app subscribes and thus gets back the processed result almost instantaneously. Simple, isn't it? To recap, Node.js publishes to out queue, to which the Python app subscribes, and the Python app in turn publishes to the in queue, to which our Node.js app subscribes, thereby enabling bidirectional asynchronous communication. By now, you're probably wondering what is it that we are building in this section. Well, let's find out.